Post-disaster victim localization via D2D communications. So this is my presentation to the IEEE PIMRC 2023. My name is Vishaka Basnaika. I'm from the Department of Computer Science, Disk Lab at UBFC. First of all, let me raise a question. How can you find victims when emergency calls are received at call centers? So during disasters in massive uh, emergency scenarios, we might face situations where we have lack of connectivity and total out of coverage scenarios. So in that case, what are the solutions that we can take to transfer an emergency calls reliably to the network infrastructure and localize the devices with acceptable limits of reliability and also with low latency? So in the general localization situations, the emergency call centers receive calls from emergency callers, and the rescuing teams are sent based on the localization estimated. So in the current literature works, multiple works have been done based on localization algorithms, and um, these works have however not considered a multi-hop device localization. They have used additional control traffic to localize the device. Apart from that, they have used scenarios. They have considered scenarios with medium or low number of anchor nodes with known location. And they have not considered scenarios where the number of anchor nodes is very low. Apart from that, the data availability is constant in those scenarios where the data uh, is limited. However, scenarios which we have in real scenarios can have progressive data availability. And then the localization algorithms such as weighted least squares localization, extended Kalman filtering based localization, particle filtering based localization, Monte Carlo based localization, and constraint satisfaction programming based localization have been used in literature works. So in these works, they have considered the measurements used by radio signals such as RSS angle of arrival, time of arrival, and satellite data such as GPS to assist in the localization. So in our work, the motivation is basically to propose a localization algorithm that is designed for scenarios with limited data availability, anchor node availability, and which uses multi-hop communications. The objectives of this work are basically, therefore, to propose a new dynamic localization algorithm that propagates location of devices through multi-hop communication data. So the proposed algorithm is known as multi-victim localization algorithm, MVLA for short. And a performance evaluation of MVLA will be done under various emergency scenarios. Performance comparison of the MVLA will be done with existing localization algorithms. So the methodology that we'll be following will be localizing multiple victims in out of coverage areas using multi-hop call data and dynamic constraint satisfaction programming method. So as overall, the steps that we'll be following will be is as given in this figure. So the multi-hop calls that are received at an emergency call center are used to extract the emergency data from the call, and the location related data such as GPS, RSSI, time of arrival, angle of arrival will be extracted. So these measurements contain some error. So depending on the error that have been observed regarding this measurement, constraints will be generated based on each of the measurements received. So all the constraints that will be generated will be considered for our constraint satisfaction program. And before running the constraint satisfaction program, we are converting the nonlinear constraints into linear constraints in order to relax the constraint satisfaction programming and give an efficient and acceptable, accurate solution of the target device. After finding the target device's location, the device's location will be updated to the rescue team after within TU time intervals. Uh, Once we go back to the steps that I mentioned as constraint generation, I would like to elaborate it further. So we once we receive GPS measurements, we can form the GPS measurement into a constraint as given in equation number 1. And further, when we talk about RSSI measurements, we can convert the RSSI measurement into distance-based constraints as given in equation number 2 and 3. So basically, we are considering that the RSSI based measurement is having a lower limit and upper limit based on the tolerance level observed of the RSSI measurement. The tolerance level is determined by the parameters such as alpha RSSI and the distance measurement based on RSSI. So the tolerance level is not only depending on alpha RSSI, but also with the distance measured. So if the distance is higher, the tolerance level is also higher. So that means that if we measure the RSSI distance between two devices which are further apart, then the tolerance of the distance measurement is going to be higher when compared to a scenario where we have the two devices really close to each other, such that the distance measurement is more accurate and therefore the tolerance level is lower. Similarly, the constraints are generated for time of arrival based distance measurement as given in 8 and 9. So the angle of arrival constraint is generated as given in this diagram and in these 5, 6, 7 equations. So the angle of arrival constraints are generated by considering the position of the angle or the angle position of the angle uh, in the circle. And so if the angle is in the second quadrant and the third quadrant, then specific constraints are developed for such scenarios because we cannot find the angle directly by taking the tan inverse function in those cases due to the sign changes that occur in the tan function in the second and third quadrant. So because of that, instead we use the sine function to get the correct constraint for the angle of arrival measurement. So once we have generated all the constraints that we require related to GPS constraint, RSSI, TOA constraints, and angle of arrival constraints, we are now going to relax the constraints that we have developed by our relaxing method. So we are going to convert the nonlinear constraints into linear constraints. So we are going to use something called a sequential linear programming method. And then we are relaxing the nonlinear constraints into linear constraints. We are going to do that for GPS, RSSI, time of arrival measurements. For the angle of arrival measurements, the constraints will remain the same. So after linearizing the constraints, we will run the algorithm as given in this block diagram. First, we will assume a solution for our constraint satisfaction problem. We will run our CSP algorithm and find a solution for our CSP CSP. And then if the solution is matching with our initial assumption, then we will stop the algorithm. If it does not match, it does not converge, then we will feed the solution that we obtained using for our CSP using our CSP back into the algorithm, and we will obtain the second solution. And then we will compare that with the previous solution. And we will keep on running this algorithm until we converge to a certain solution. So this procedure will be repeated for each device in the multi-hop communication until we localize the target device. So once we consider an example scenario, we can consider a situation where we are trying to localize a device M3. Once that M3 is transmitting a multi-hop emergency call towards the network infrastructure. So once we receive the multi-hop communication data, that data will be used to generate multiple constraints as given in step number 1. And that set of constraints will be used to first localize the device which is more closest to the base station and which has higher localization accuracy, which is M2. And then M2 will be localized, and that localization will be given as constraints. Those constraint set also will be added to the initial constraint set, and secondly, the location of M1 device will be found. Once we find the M1's location, that that constraint set will be also available, and it will also help in localizing the third device, which is M3, and M3's location will be determined based on all the constraints that we have created thus far. So this same algorithm will be used for large scale scenarios where there are about 15,000 devices in the network area and about 100 to 3,000 emergency devices in the area. Apart from that, we are considering the simulation for such kind of a situation, and we have considered a city area of Connecticut in USA, and we have considered that there are about 7 functioning base stations or GNBs in the network area and about 26 non-functioning or non-working base stations in the area. We have considered other simulation parameters as given in this table, and then confidence levels in the measurements we have taken as given in this table. Then we have the evaluation parameters that we have defined as average distance error and the computing delay. So average distance error means basically we are taking the average of all the distance errors that we observe with each of the target emergency devices with their real location and the estimated locations. So the distance error or the distance between the target location, target device's actual location and the estimated location is taken as the distance error. So the average of such distance errors or the number of emergency devices that we have considered is taken as the average distance error. Next, when we consider about the computing delay, we can find the computing delay by taking the difference between the time where we are updating the location of the target device to the time that we have received the data, received the multi-hop communication data at the center, emergency center. So the first result shows us how the performance of the proposed algorithm varies once we have a high number of radio data available. So rather than having only GPS measurement, once we have all the types of measurements, GPS, RSSI, time of arrival, and angle of arrival, we can obtain lower localization error. So we were able to observe a localization error of 163 to up to about 167 using this MVLA proposed method. And then once we have lower measurement errors, then we can have higher localization accuracy and average lower localization error. Apart from that, we compared our method with existing algorithm known as RSSI-MCL. It uses like particle filtering based method. It uses GPS and RSSI based method to form anchor boxes and estimate the location of devices. So when we compare our proposed algorithm with the existing RSSI method, we were able to observe that the average distance error in our proposed method was lower than the RSSI-MCL method. So one reason is the usage of particle filtering based method, which uses particles to estimate the location of the target devices. If the number of particles are not enough, then the localization error can increase. So in our method, we use some constraint satisfaction based method. So if the number of constraints are high, we are able to obtain a lower localization error. If we know the confidence levels of the measurements, uh, 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 and we are able to like restrict the area of the target device, we are able to achieve high localization accuracy and lesser error. We are also able to reach a delay of below 10 seconds using our proposed method, while there's a delay of 100 seconds with the RSS MCL method. And once we have the number of functioning base stations reaching 10, we have an error of below 200 meters using our proposed method, while we have an error above 230 meters in the existing RSSI MCL method. So as a conclusion, our method is more feasible since we can obtain data measurements of GPS, RSS, angle of time of arrival measurements, even using smartphones. And we are able to take experimental data using the experiments that we have already conducted, then we can find the confidence level of the measurements. We can also obtain more reliability with our proposed scheme, about 55.9% than RSS-MCL. That means more accuracy than the RSS-MCL. And then we have lesser computational delay than the existing method. So we have delay of less than 10 seconds. And then we have update efficiency about 90% higher than the RSS-MCL. We have some future works of localizing moving devices with this work. And then we have to also consider about the impact of constraint linearization. So with that, I would like to end the presentation. So thank you.